In this video, I'll start the third major separation technique that we'll cover in ECH 3023. It's called liquid-liquid extraction. And the premise of liquid-liquid extraction is similar to absorption stripping in that it doesn't seek to separate two things, but rather to transfer some solute into another stream. So let's imagine that we had a liquid stream that had some solute in it. We'll call that the feed. And we'll also talk about vocabulary in this video as well. So the feed consists of some solute, which is the thing that we want to extract from the rest of the stream, which is called the diluent. Or the thing that is diluting the solute is how I like to think of it. That feed will be fed to a mixer where it will be contacted with a stream of some solvent. So similar to absorption stripping, we're adding a third phase. And the solvent is important because it must be at least partially immiscible with the diluent. So we'll talk about that a little bit later. Inside the mixer, we're going to have some mechanical agitation. So the mixer obviously will mix this stuff up really well. And the feed and diluent will contact each other. And the idea is that the solute will transfer from the diluent-rich phase to the solvent phase. So after the mixer, we have what's called a temporary emulsion that gets sent to another process unit called a settler. A temporary emulsion, by the way, means that all three components, the solute, diluent, and solvent, are all mixed up together. And in the settler, what's happening is that it's just allowed to sit. So phases allowed to decant. And in this phase, there's no mechanical agitation going on. So unperturbed. And out of the settler will emerge two streams. One of them is called the raffinate phase. And this is the diluent-rich stream, which will still have some residual solute. And the other stream is called the extract. And the extract is the solvent-rich phase. And this contains extracted solute. And if it's a good liquid-liquid extraction process, it'll contain most of the solute. So once again, like I said, we're not separating anything technically. We are just transferring the solute from the diluent phase to the solvent phase, the extract. Okay, so some things I want to touch on here is, first of all, solvent selection is very important for liquid-liquid extraction. The first item that must be true for solvent selection is that it must be partially immiscible with the diluent. At least partially immiscible, if not fully immiscible. And if this word is unfamiliar, immiscible means that it cannot mix. So I'm thinking of oil and water. Or salad dressing is another good example. Like a nice vinaigrette dressing is an example of a partially immiscible system. So in vinaigrette dressing, you have an oil phase and a water phase. And if you let it sit in your fridge for too long, it will separate, which isn't a problem. But you can get it to form a temporary emulsion by mixing it or shaking it. And that's when you would put it on your salad. So this is what I think about when I think of liquid-liquid extraction. This is also a common experiment that you would run in organic chemistry. So I'm thinking of an experiment that I did in my Orgo lab with a separatory funnel. So you can run liquid-liquid extractions with a separatory funnel as well. And this is the same thing that we're talking about, but as chemical engineers, we just scale it up. So we're not doing it in a separatory funnel, but we're doing it in chemical engineering process equipment that is many times the size of the separatory funnel. The ramifications if you don't. So if not, all you have is a mixture of three things. No phase separation occurs. So you can imagine if you started with a solute and diluent and you added a solvent that was miscible and you mixed it all up, you would just have a mixture of now, instead of two things, you would have three things. So that is the opposite thing of what we want to occur. No phase separation occurs. But the second item I wanted to mention under solvent selection is that the solute should have high affinity for the solvent. Should have high affinity. It's not a huge problem if not. If not, though, you need more solvent. High affinity for the solvent. And the word affinity means that it has an attraction to it. So you want the solute to be very soluble in the solvent. So here I think of like a magnet. So if the solute were some iron filings or something, you want the solvent to be a very strong magnet to pick up all those filings. You don't want the solvent to be a weak magnet because then you'll need more of it in order to extract the same amount of solute. This is not necessary, as I just said, but the higher the better. And this is for efficiency. For efficiency. And the last properties we want of the solvent selection is that it is preferably non-hazardous. And the reasons for that should be clear from your safety course. Remember, in your safety class, you always hear about making your process inherently safer. And selecting a safer solvent would be one example of how you can do that. Inherently safer processes. It should also be cheap, preferably. In that order, right? Non-hazardous is more important than cheap. And easy to separate from the solute in post-processing. Unless for some reason you wanted to keep the solute in the solvent. From the solute in post-processing. But thinking about the overall goals of the process, it doesn't do you any good to have the solute in the solvent, right? Ideally, what you would want to do is then send this extract to some post-processing where you can isolate the solute and then you can recycle the solvent, and that works better economically. If you have to throw away all your solvent, that's very wasteful. It also depends on what the goals of your process are. If your solvent is water, for example, and you don't, it's cheap relatively, it doesn't really matter if you throw it away if your solute is non-hazardous. But it also depends on if your goal is to clean the diluent or if it is to extract the solute. You can have liquid-liquid extraction processes where the goal is either one. So a typical process flow diagram for a liquid-liquid extraction process would kind of look like the diagram that I've shown you above, except the only difference is we don't really care about this temporary emulsion. Just like the other separation processes that we've studied, we're going to be doing multiple such stages. And if we have to draw two process unit for every stage, that's going to become quite cumbersome. So typically the Mixer-Sedler unit is drawn together. So this is what my process flow diagram would look like for a single stage Mixer-Sedler. Mixer-Sedler I abbreviate with just an M/S. We have a feed that has some amount of solute. I call the solute my component A because solvent is going to be my S. So I call that XA for the feed. And I also have some XD for the feed, where A stands for solute, D stands for diluent. I also have some amount of solvent, that is my S. And typically my XS of the solvent stream is 1, usually. Right, if I'm recycling solvent, then obviously that won't be the case. Out of my Mixer-Sedler, I'm going to have an extract stream, which I will term E for extract. And by the way, Fs, E, and R will be the other one, are going to be molar flow rates, so moles per time. I'm also going to have to deal with my mole fractions. So I'm going to have XA in the extract, XD in the extract, and XS in the extract. And this is if my system is partially miscible. We're going to be talking about partially miscible. Remember, my extract is mostly solvent, but I can still have some diluent in there as well. So you'd expect that the mole fraction of solvent would be greatest in the extract stream, but I still have a non-zero mole fraction of diluent. And similarly, I have XA for R, XD for R, and XS for R. All right, so I have all three things in each stream, even though the raffinate is going to be primarily my diluent. So just like all other separation processes, solving problems related to liquid-liquid extraction is going to involve simultaneous solution of the material balances and the equilibrium data. The material balances, you should be getting to the point where you can derive this without me having to show you. F plus S is equal to E plus R. That's my overall solvent, well, overall material balance. And then I also have a material balance for A, D, and S. See if you can pause the video and derive these on your own. My A material balance is XAF times F is equal to XAE times E plus XAR times R. And similar thing for the diluent. XDF is equal to XDE times E plus XDR times R. And my solute would be S, and then obviously times XSS if it is not 1 equals XSE times E plus XSR times R. And typically, once again, in separation processes, we typically know what both feeds are. We know what the feed is, and we know how much solvent we want to feed. Or actually, that is going to be one of the unknowns, the potential unknowns in this process. We might ask, how much solvent do we want to feed to this process? So the number of unknowns here might change, but you can imagine how we're going to have more unknowns than equations just from looking at this system of equations. So where do the other constraints come in? You've probably guessed by now, it's from the equilibrium data. And I'll introduce the equilibrium data in the next video.